Right now, your ear is performing a mathematical operation that took humans 200 years to figure out. Every sound you've ever heard, every song, every voice, every thunderclap, has been silently decomposed into pure sine waves by a biological computer inside your skull. You don't hear sound. You hear a spectrum. And the equation that describes it runs your music apps, your noise-cancelling headphones, your phone calls, and quantum mechanics. Most people would say sound is just vibrations in air. That answer is almost completely wrong. By the end of this video, you'll know what sound actually is, physically and mathematically, and you'll understand the 1822 equation that turned out to describe almost every wave phenomenon in the universe. This is going to get a little dense in the middle. Stay with me, the payoff is worth it. You already know sound is a pressure pattern in air. Molecules push their neighbors, the pattern propagates, the air itself stays put. Like a stadium wave. Fine. The interesting question isn't what sound is. It's how you describe one mathematically. And the answer to that, starting in 1822, broke physics open. Let's start with the simplest possible sound, a pure tone. A flute playing one note. A tuning fork. This sound is mathematically perfect, it's a sine wave. One equation describes it completely. Y of t equals a times sine of 2 pi ft plus phi. Where A is amplitude, how loud. F is frequency, how high or low. Phi is phase, where in the cycle it starts. And t is time. 3 numbers and you've fully described that sound. Now the problem. Real sounds aren't pure tones. Your voice isn't a sine wave. A piano isn't a sine wave. A clap, a bird, an orchestra, these are messy, wildly complex pressure patterns that look like chaos. For 200 years, mathematicians and physicists asked a brutal question: can complicated sounds be described mathematically at all? Or are they just irreducibly messy? The answer came in 1822 from a French mathematician named Joseph Fourier. And it changed physics forever. Fourier proved something nobody believed. He proved that any periodic signal, no matter how complex, no matter how messy, can be expressed exactly as a sum of pure sine waves. Not approximately. Exactly. This is the Fourier series, a constant term, plus a sum of cosines and sines at integer multiples of a base frequency. The coefficients, those a sub n and b sub n numbers, are the recipe. They tell you how much of each pure tone to mix together to rebuild the original. Here's exactly what that means. Take a square wave. A signal that jumps between two values, on, off, like a digital clock. Fourier's theorem says I can build this jagged shape out of smooth sine waves. Here's how. Start with one sine wave at the base frequency. Smooth curve. Looks nothing like a square. Add a second sine wave at 3 times that frequency with 1/3 the amplitude. The shape gets steeper. Add another at 5 times the frequency, amplitude 1/5. Sharper. At 7 times, amplitude 1/7. At 9 times, 1/9. Keep going, and the sum converges exactly to a square wave. That recipe, odd harmonics with amplitudes 1, 1/3, 1/5, 1/7, and so on, is the Fourier series for a square wave. Every periodic signal has its own unique recipe of coefficients. That's all a Fourier series is. Let me show you what frequency domain actually means, because it's the whole point. Here's a pure tone, one sine wave at 440 Hz, plotted in time. It looks wavy. Now plot the same sound differently. On the x-axis, put frequency, not time. On the y-axis, put how much of each frequency is present. Result, one tall spike at 440 Hz. Nothing else. That's the entire sound. That picture is the frequency domain. Now add a second tone at 660 Hz. In time, the waveform looks messy, wavy on top of wavy. In the frequency domain, 2 clean spikes. For 40 and 660. That's it. Time hides the structure. Frequency reveals it. Stop and think about what this means. Sound is not fundamentally messy. It just looks messy when you plot it in time. Plot it in frequency, and the structure appears. We've been measuring sound in the wrong space the whole time. Fourier series only works for signals that repeat, like a held musical note, or that square wave we just built. Both have a fixed period that goes on forever. But most real-world sounds don't repeat. A hand clap is one burst, and it's gone. A spoken word lasts half a second and never comes back. A song changes constantly. So how do you find the frequency recipe of a sound that happens just once? That's where we need a more powerful tool, the Fourier transform. It's the Fourier series stretched to handle any signal, periodic or not. The equation. Capital F of omega equals the integral from minus infinity to infinity of f of t times e to the minus I omega t, dt. Hang on, let me decode it. F of t is your sound pressure as a function of time. Capital F of omega is what you get out, how much of each frequency omega is in that sound. That e to the minus I omega t? It's a spinning complex exponential. Mathematically, e to the I theta equals cosine theta plus I sine theta, Euler's formula. So this spinning thing is just a way of asking the signal, do you contain a sine wave at frequency omega? The integral multiplies your signal by this spinning probe at every moment in time, then adds up all those products. If your signal has a sine wave at that frequency, the products line up and add to a big number. If it doesn't, they cancel to zero. In one operation, the Fourier transform asks every possible frequency, how much of you is in this sound? The output is a complete spectrum, the recipe of sine waves. This single equation underlies modern signal processing, image compression, quantum mechanics, and the entire field of communications engineering. It's one of the most important results in mathematics. Full stop. Let's run this on real sounds. A tuning fork. You hit it, it rings. Its waveform in time is a clean sine wave. Its Fourier transform, one tall spike at the fork's frequency. Nothing else. That's the simplest possible case. Now a hand clap. In time, it's a sharp burst, milliseconds long, then silence. Its Fourier transform, a broadband spectrum. Energy spread across many frequencies. Short bursts in time become wide bands in frequency. Now the spoken vowel R. In time, it's a complicated, almost repeating wave. Its Fourier transform shows sharp peaks at specific frequencies, around 700 Hz and 1200 Hz. Those peaks are called formants. They're set by the shape of your throat and mouth. Every vowel has its own formant pattern. That's how your brain tells a R apart from an E. Same equation. 3 completely different signals. 3 completely different fingerprints. That's the power of the Fourier transform, it gives every signal its unique frequency identity. Here's the part that should freak you out. Inside your inner ear, there's a spiral structure called the cochlea. It's about the size of a pea. Inside, along its length, sit roughly 16,000 hair cells. Each hair cell is physically tuned to vibrate at a specific frequency, high frequencies near the base of the spiral, low frequencies at the tip. When sound enters your ear, the cochlear's fluid mechanics naturally cause different frequencies to peak at different positions along the spiral. The hair cell at each position fires when its specific frequency is present. In other words, your ear physically performs a Fourier transform. It doesn't send sound to your brain. It sends a spectrum. Your brain receives parallel signals across 16,000 frequency channels, then reassembles them into the perception of music, speech, or noise. You don't hear sound. You hear a Fourier transform of sound. Evolution discovered Fourier's equation hundreds of millions of years before he did. Once you can convert any signal into its frequency recipe, you can do things that seem impossible. Shazam recognizes a song in 2 seconds by Fourier transforming the audio, finding the loudest frequency peaks, and looking them up in a database. It doesn't compare audio at all, it compares spectra. MP3 compression works by taking your music's Fourier transform, throwing away frequencies your ear can't hear well, and storing only the rest. A 30 megabyte song becomes 3 megabytes with no audible difference. JPEG compression does the same thing for images, applied to 2 dimensions instead of 1. Noise-cancelling headphones Fourier transform incoming noise in real time, then generate the inverse spectrum to cancel it. Every Wi-Fi signal, every radio broadcast, every 5G transmission encodes data into specific frequencies and demodulates them with a Fourier transform on the other side. It goes deeper. The Fourier transform is mathematically equivalent to the relationship between position and momentum in quantum mechanics. The Heisenberg uncertainty principle is literally a consequence of Fourier's math. MRI machines work by Fourier transforming radio signals from hydrogen atoms in your body. Astronomers analyze starlight using Fourier transforms to determine what stars are made of. One equation, discovered while trying to understand heat flow, turned out to describe almost every wave phenomenon in the universe. One more layer. Your ear doesn't just do Fourier transforms, it processes the output logarithmically. Loudness is measured in decibels. dB is a logarithmic scale, every 10 dB is 10 times more sound intensity. A whisper is 30 dB. A normal conversation is 60 dB, 1,000 times more intense. A rock concert is 110 dB, 100 million times more intense than the whisper. But it doesn't feel 100 million times louder. It feels maybe 100 times louder. Because perception is roughly logarithmic. Pitch is the same. Each octave in music is a frequency doubling. Middle C is 261 Hz. The C above it is 522 Hz. The C above that is 1044 Hz. But your ear hears them as equally spaced. Your auditory system computes logarithms in real time. So here's the big idea. Sound was the first wave humans really understood. We knew it could be modeled by sine waves. We knew about frequency and amplitude. We could write the equations. But when Fourier proved that any signal is a sum of sine waves, something deeper happened. The same math turned out to describe light. Then radio. Then quantum particles. Then heat. Then financial time series. Then images. Then neural signals. It turned out the universe doesn't have sound math and light math and quantum math. It has wave math. And Fourier figured out the operating system. So when you hear a song, here's what's happening. A speaker vibrates, sending pressure patterns through the air. Those patterns enter your ear, travel into the cochlea, and physically separate into frequency components. Your brain receives parallel signals from 16,000 hair cells, each reporting on one slice of the spectrum. Your consciousness reassembles those signals into the experience of music. There is no sound in your head. There is a Fourier transform, running constantly, biologically, automatically. The thing you've called hearing for your entire life is actually one of the most sophisticated mathematical operations in all of nature. Now, knowing this, you can finally understand something that seems like magic, how Shazam recognizes a song in 2 seconds from 100 million possibilities, in a noisy bar, with people talking over it. Without comparing audio. Without listening to the song. The answer is in the math you just learned. In the next video, I'll show you the exact algorithm, how Fourier transforms become audio fingerprints, and how those fingerprints get found in a database of 100 million in 0.3 seconds. Subscribe so you don't miss it. Comment sine wave if you made it this